This is Chapter 7, Problem 34. In this problem, we have a 10 kilogram brick moving along the x-axis with a variable acceleration. Because the acceleration isn't constant, we can't find the work done simply by multiplying the force times the displacement. We talked about in class how you can integrate the force with respect to position in order to find the work done, and that's the same thing as finding the area under the curve if you remember all of our calculus lessons. Here we have the graph of the acceleration as a function of the position. We know that the upper limit of that graph is AS, and AS is equal to 20 meters per second squared. We can make this graph of acceleration as a function of position into a force as a function of position graph simply by multiplying the mass times the acceleration. So in this case we would have the upper force, Fs, is equal to 20 times 10, mass times the acceleration, or just 200 newtons. Our graph is going to have the exact same form because all we're doing is multiplying the acceleration by the mass. So now we're going to get a graph that looks like this. And now the upper limit of that graph, let's call that Fs, and that's the 200. And this is a function of the position. And we're trying to find the work done as we move from 0 meters to 8 meters. I see two different ways of solving the problem from this point. You could find the slope of the graph and then just integrate the function, or you could see that we're dealing with a triangle here and we're trying to find the area under the curve, this shaded region right in here. The area of a triangle is equal to 1/2 the base times the height. So in this case the area would be equal to 1/2, the base is equal to 8, and the height is equal to 200. And so we get that the area, which is the same thing as the work, is equal to 800 joules. And that's it.